Hey folks, wanted to create a quick video about the periodic table of elements based on our classroom the other night and talk about some of the things going on with the periodic table and why it can be a useful tool for us. So the first thing I want to talk about is the concept of groups and periods. Groups are areas of the periodic table which are completely aligned vertically. Okay, so a group would be something that was all in the same vertical column right here. Okay, so if we look at it from this perspective, all these things right here are groups. Okay, the thing about a group that's nice is that generally speaking, things that are in groups have very common properties, and we'll talk about one of those properties in just a couple of minutes. As a result of them having common properties, some of these groups have special names that are associated with them. So this first group right here, which is called group 1, okay, group 1A in fact, they're referred to as the alkali metals. Okay, the exception to that is hydrogen, because hydrogen is not a metal itself altogether. It's placed there for a reason I'll talk about in just a couple of minutes. Things that are in group 2, or group 2A as it's referred to, are referred to as the alkaline earth metals. Then we can skip way ahead and we can talk about group 7A. Group 7A, and anything else in this group right here, are referred to as the halogens. And group 8A, anything in this group right here, are referred to as the noble gases or the inert gases. One thing I sort of was alluding to just a moment ago is this concept of group A, group B. What I want to point out is that the periodic table is also organized in fashion of groups, okay? And we talked about this the other night, but I want to just give you a visual. Group A are the elements that are not included in these boxes that I've just drawn here. The thing about group A is that things that are in group A generally follow common properties. They're pretty straightforward to understand. Things that are referred to as group B elements, or the things that are in these boxes right here, are also referred to as the transition metals. The purple ones here are simply called transition metals. Those that are pink down here are referred to as the inner transition metals. The reason that we pull those two groups out and give them their own set of rules associated with them is based on the fact that they have expanded electron shells, and because they have expanded electron shells, they sort of have some of their own properties that are associated with them, and they have some of their own rules associated with them, some of which we'll talk about in the next class. To talk about periods now, periods are arranged horizontally. Okay, the way that I like to remind people is at the end of a sentence that you would write horizontally, you'd put a period. And so when we align these, anything within a period, what's interesting about them is they all have electrons that are in the same energy level. The period numbers down the side indicate the energy level which we can find electrons in. So something in the second period right here would be something that has electrons in the second energy level. Something in period 5 here has electrons in the fifth energy level. What's interesting about that is that the highest energy level that we see for something, so something that would be in group 5, would have a total of 5 energy levels. The fifth energy level, or the outermost energy level, is referred to as the valence energy level. Okay, so again, I want to point out something in group 5 also has energy levels 4, 3, 2, and 1, but the thing that makes the fifth energy level significant is it's referred to as the valence energy level. Okay, why is this important? Well, because as you go across the periodic table from the alkali metals all the way to the noble gases, you have a series of repeating properties. Okay, so the alkali metals, generally speaking, have properties to say that they are very soft, very reactive metals. As we move across the line, we can see that we're going from very metallic to turning into a nonmetal to very nonmetallic. Okay, the halogens are very reactive nonmetals, and the noble gases are non-reactive elements at all. Well, what's interesting about this is as we go across, we go from very reactive metal down to very reactive nonmetal to non-reactive nonmetal called a noble gas. And in order for us to restart again, we would go back to the beginning on the next row, very reactive metal, working our way across, very reactive nonmetal, non-reactive nonmetal. And we start again. Very reactive metal, working our way across, very reactive nonmetal, non-reactive nonmetal. So it's a repeating pattern over and over again. The other thing that repeats over and over again has to do with the valence electrons. Okay, so I'm on a new page now, valence electrons. Valence electrons are electrons that are in the valence energy level. So a few moments ago I talked about how the outermost energy level is the valence energy level. The electrons that are found in that energy level are referred to as valence electrons. We count valence electrons of the A group going across from left to right. So something that's in group 1 has 1 valence electron. That's why hydrogen is positioned where it is, because hydrogen has to have 1 valence electron, and that's why it's there. I said a moment ago that hydrogen was not considered an alkali metal like everything else. However, it's placed there because of its 1 valence electron. Group 2 elements have 2 valence electrons. Group 2A elements have 2 valence electrons. We skip over the transition metals again because we talked about how they have their own special set of rules that are associated with them. Group 3 elements have 3 valence electrons. Group 4 elements have 4 valence electrons. Group 5 elements have 5 valence electrons. 6A have 6, 7A have 7, and 8A have 8 valence electrons. What's going on here is that pretty much we have to point out the fact that the noble gases, these guys right here, we talked a moment ago on the previous page that the noble gases were very non-reactive nonmetals. They're inert nonmetals. They don't do anything at all. Elements don't like to react as if they have a choice, but the reality is that elements would prefer to be non-reactive. So what's going to happen is the desire for all elements are to look like a noble gas, or at least have the same number of electrons as a noble gas. What makes a noble gas inert or non-reactive is the fact that it's got its full its valence electron shell is completely full. So what's interesting about that is we talked about how group 1 elements have 1 valence electron, group 2 have 2 valence electrons, and all the way across. Well, the thing about it is, if something in group 1 has 1 valence electron, let's talk about lithium for just a second. It's got 1 valence electron. If it wants to look like a noble gas so that it can be non-reactive, one of two things can happen. It could either gain 7 valence electrons, 1, 2, 3, 4, 5, 6, 7, to look like neon, or it could lose 1 electron, 1 valence electron, from 1 valence electron to 0 valence electrons in the second energy level to look like helium. Now the key is if it loses 1 valence electron in the second energy level, remember there are still electrons in the first energy level. Okay, so if it loses the 1 in the second energy level, that means it's got 2 in the first energy level and it looks like helium. The thing about it is that these elements will do what is more energetically favorable to do, and the easiest way to understand what's more energetically favorable is to very simply consider how many spots you would have to jump to get to 8. So lithium would have to jump +7 by gaining, I shouldn't say +7, lithium would have to increase by 7 electrons in order to look like neon, or it could decrease by 1 electron to look like helium. Because it's easier to lose 1 electron, it's going to look like helium, and as a result, lithium will have a +1 charge. That same thing goes true for potassium as well. Again, neglecting the transition metals, we know that potassium could either gain 7 electrons to look like krypton for its valence electron shell, or it could lose 1 electron to look like argon. It will be easier to lose that 1 electron, giving it a +1 shell. Well, how does it get a +1, okay, if it's losing an electron? Well, keep in mind, neutral potassium will have 19 protons. Neutral potassium will also have 19 electrons. Well, if we lose that 1, if we take 1 electron away, it's still got 19 protons, making it potassium, but now it's only got 18 electrons. So in essence, you have 19 positives, 18 negatives. You've got 1 more positive than you do negatives, and therefore you have a +1 charge. Things in group 2 will have a +2 charge because for the same reason, something like magnesium could either gain 6 electrons, 1, 2, 3, 4, 5, 6, to look like argon, or it could lose 2, 1, 2, to look like neon. Again, if we take both of those electrons away, it has 0 electrons in the third energy level, but it's got 8 in the second energy level. Okay, and as a result of it having 8 in the second energy level, it looks like neon, and as a result of looking like neon, it will behave like neon. In essence, it will have an inert noble gas electron shell. Okay, now the same thing takes place for group 3 elements. They'll have a positive 3 charge, but something a little different takes place when we talk about the nonmetals. Okay, if we talk about fluorine for a second, fluorine we know is going to have 7 valence electrons because it's in group 7 of the periodic table. It's easier to gain 1 electron to look like neon than it would be to lose 7 to look like helium. Because it's gaining 1 electron, it's going to have a -1 charge. Oxygen will gain 2 electrons to give it a -2 charge, and nitrogen will gain 3 electrons to give it a -3 charge. Things that are in group 4 will neither gain nor lose electrons easily. Something like carbon, for instance, could either gain 4 electrons or lose 4 electrons, and as a result, they will do neither and they will not form ions. Okay, it's really important to understand that these valence electrons are what are going to allow these elements to turn into ions, which are essentially elements that have a charge associated with them. We're going to talk about ions at the next class. One last thing I wanted to talk about were the physical properties of elements. Now, because everything that's in group 1 will easily lose 1 valence electron, that means all of those elements in group 1 are going to have common physical properties. So for instance, they're all very soft, very reactive metals. Okay? As you go down the group, they actually become even more reactive. So sodium is a very reactive metal, potassium is even more reactive than sodium, and so on and so forth. Okay? Things that are in group 2 will behave similarly as well because they all have 2 valence electrons. Things in group 7 behave similarly because they have 7 valence electrons. Things in group 8 will behave similarly because they all have 8 valence electrons. The other thing to keep in mind is that we have to understand that generally speaking, there's a barrier that exists between metals and nonmetals. And I'm going to see what I can do quickly here about drawing in this barrier the way that I want it to look. But basically, this barrier is formed according to the staircase line right here. Okay, and the staircase line naturally separates your metals from your nonmetals. And you can see that there's a little key at the top here. Shows metals are bluish in color, semi-metals are reddish in color, nonmetals are green in color. Anything that is to the left of that staircase line, anything to the left of the staircase line are going to be your metals. So these are all metals all in here. Okay, anything to the right of the staircase line are going to be nonmetals. I know it's a little hard to see, but anything that aligns the staircase line are going to be semi-metals, or we use the term metalloids. Metals will always lose electrons to form positive ions. Nonmetals will always gain electrons to form negative ions, and semi-metals follow their own rules, kind of like the transition metals, in that there's no affinity to gain or to lose electrons. There are also special properties associated with semi-metals that allow them to have special characteristics. And we may or may not talk about those later on this year, but suffice it to say that the semi-metals really serve as a nice barrier between metallic and non-metallic character. They allow for the transition from metals to non-metals. As you read across, you can see that we go metal, 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 semi-metal, semi-metal, non-metal. And that's generally speaking the same thing that happens as you go across the periodic table, again dealing with those repeating patterns over and over and over again. Within the metals, they're generally all solids with the exception of mercury. Okay, mercury is a liquid metal. Actually, mercury, Hg, comes from the term hydrogyrum, which actually means liquid silver, which is kind of interesting. And it makes sense. If you've ever seen mercury before, you know it's a liquid metal and it looks like silver. The other liquid on the periodic table is bromine. Bromine is a non-metal that is liquid. So all metals are solid with the exception of mercury. Non-metals can either be solid or gas with the exception of bromine, which is going to be liquid in character. The last thing to point out is that the majority of the elements on the periodic table are naturally occurring. Anything that has a solid symbol on it would be indicative of a naturally occurring element, but there are a couple, Copernicum for instance, which is recently named, Hassium, Seaborgium, all these elements right here that have their symbols in an outline, those are synthetic elements. That means that they are formed as a result of work in a lab or something like that. They're not naturally found. So that's important to keep in mind as well. I hope this little video helped you to gain an appreciation about some more of the periodic table. There's a lot of information. Hopefully the 15 minutes or so that you saw this video is enough to give you a good idea of what's going on. Certainly it allowed us to buy 15 more minutes of class time to work on some other things. And if you have any questions, please feel free to get a hold of me, either through email or by seeing me before class next time, and we can go ahead and talk from there. Okay, so I hope you all have a great day. Please try to be safe, and we'll see you all real soon.